We're going to hear now from our industry partners, and their support helps us with many aspects of our work here at the Institute, including funding workshops and the postdoc stipends and many other things. So thank you for all your support. And we're really happy that each of our industry partners has a representative here today to tell us about their work. And speakers' talks are 15 minutes, and we have Carson minding the clock here. She'll give you a 5-minute and a 2-minute warning. So that 15 minutes includes questions and the setup time and stuff. So it's a pleasure to have Sanjam Garg with us today, telling us about zero-knowledge SNARKs as a service. So welcome.
Thank you. Yeah, thanks for the invitation. I'm Sanjam. It's really fun to be here in Simons representing NTT. So it's pretty fun. So I'll be talking today about zero-knowledge SNARKs as a service, or what we call ZK-SAS. This is based on joint work with Arushi, who's also at NTT, Abhishek Jain, who's at Johns Hopkins, Guru Vamsi Policharla, and Shruti Sekhar, who are at UC Berkeley. Okay, so let me remind you what SNARKs are, or zero-knowledge succinct non-interactive arguments of knowledge are. It's a bit of a mouthful, so I'll go slowly over it, and hopefully by the end of it, it'll be clear. So we have a prover and a verifier, and the prover wants to convince the verifier that a certain computation C on input X and W outputs 1. So that's what the prover wants to convince the verifier. The prover gets this input X and W. X is called the statement, that's what we call the statement, and W is what we often refer to as the witness. It's sort of the secret input that the prover has. And the verifier only has access to the public part of this which is X. And the actual computation we want to perform, the circuit C, or whatever other model of computation you want, is also public. Our prover computes a proof pi and sends to the verifier, and the verifier at this time either outputs accept or reject. Accept meaning he accepts the prover's claim that the circuit or this computation C on input X and some value W outputs 1, and outputs reject if he rejects this claim. Okay. So in short, what this proof pi is supposed to be is a privacy preserving short certificate attesting to the correctness of this computation. Okay. So let me go over each word here and kind of elaborate on what they mean and how they relate to the nomenclature of SNARKs, the zero-knowledge succinct non-interactive argument of knowledge. So the privacy preserving part means that this proof pi that's sent to the verifier does not leak information about the witness W. In other words, the prover keeps W hidden, and that's where the zero-knowledge word comes in. The short aspect of the certificates represents the succinctness in the name, which is that the time to verify, and thereby also the size of the proof pi that the prover sends to the verifier, is small. We definitely want this proof to be sublinear in the time it takes to compute the circuit, this computation C, so it should be smaller than. So the verifier should have to spend less time than the prover does. Ideally, we typically kind of want the size of the proof and the verification time to basically be independent of the computation it takes. Maybe this computation takes a year, but the verifier can verify in a few milliseconds. We want these to be certificates. So if you're familiar with this area, there are other forms of zero-knowledge proofs which involve interaction. Here we want these to be certificates where the prover once issues this proof to the verifier can go around, give this certificate to others, and they would also be equally convinced that this computation was done correctly. Okay, and the final thing is this proof attests to the correctness of this computation. In particular, a cheating prover, a malicious prover, cannot convince a verifier that a statement is true. In particular, it cannot make a verifier output accept if the statement is actually false. If there does not exist a value W such that the circuit C X on all possible inputs outputs 0, then the verifier will not accept this proof. And I'm kind of cheating here. The property is a bit stronger. It's not just an argument, but argument of knowledge. In fact, the proof certifies that not only that there exists this value W, but in fact the prover knows it. Okay? So this is what zero knowledge, succinct, non-interactive arguments of knowledge are. And they've been immensely, we've been studying them for over, since '92, so a fair bit of time. But they have kind of really in the last decade become of significant interest and tremendous amount of applications. I'll just describe at a high level a few very important ones. The first one actually goes back to a vision from David Chom in the '80s, where he talked about anonymous credentials. Think about going to a liquor store and proving to the cashier that you're above 18 without disclosing to them your name and date of birth, which is typically written on your driver's license and which you typically do share. So that's sort of the digital analog is anonymous credentials. ZK-SNARKs make this, there are other ways to do it, but ZK-SNARKs also enable some of these applications. Privacy preserving crypto. So you want, if you've heard about there's sort of no privacy on Bitcoin. If you make any transactions, if I send you $10, then they can effectively be traced. We can use ZK-SNARKs to add privacy, at least to some extent. For example, Zcash does. In the same way, we have private smart contracts, which allow for executing smart contracts on things like Ethereum in a privacy-preserving way. And finally, sort of a very cool application, which is not related to cryptocurrency, is sort of fighting disinformation. So, for example, let's say there's a picture taken in Ukraine by a particular camera, and the camera generates the picture with a signature that this image was taken at a particular latitude and longitude using the GPS information it has access to. You can take that picture and give a proof that it was taken somewhere in Ukraine without leaking exactly where it was. So you could sort of attach a ZK-SNARK that allows you to do that. So in an effort to fight disinformation. And these are some example applications, but they're sort of now already multi-billion-dollar companies which are trying to kind of commercialize on ZK-SNARKs or associated technologies, the techniques that are developed. So this is sort of really growing very rapidly. And by the way, this is just like I put 3 examples, the many of these companies. Okay, so what is sort of the main, there's sort of a lot of research that has gone, and over the last decade we have seen tremendous improvements, but still the key bottleneck in using these completely ubiquitously is prover runtimes. So if the original computation that you ran, let's say in time t, if you wanted to generate a ZK-SNARK for that, it would take roughly 250 to 500 times the time to generate the proof. And this is quite expensive. And I'm not talking about all circuits. This is sort of the typical circuit that people are using and the numbers we see. And this overhead becomes even bigger when we're talking about as the size of the computations becomes larger. So this is not sort of linear factors. And part of the reason is as the size of the computations become larger, the memory overheads become larger. You have to keep all this large amount of information in memory. And there are page faults and so on, which pushes proof times to be even larger. So our goal has been to kind of, and this is sort of for the community as well. There are a lot of people working on this goal in trying to generate proofs or realize proof systems which will prove faster. Okay, and there are many techniques being discussed here. The specific path that we will try here is, can we use software as a solution to generate these SNARKs faster? So can I outsource the computation to someone else to do it? And you can imagine, maybe trying to generate a ZK-SNARK on your phone. I'm sending you $10. I want to generate a proof for that. They'll go on some blockchain application, and you want to kind of post that on the blockchain, and you want to generate this proof quickly. Okay. So a very nice work that tries to sort of in a similar way do this is the DZK work. What this work does is that I'm trying to generate a SNARK. Okay, I'm computationally constrained. Why not let me go out and hire a cluster of computers that will do it faster for me? This is exactly what this work does. And they're able to achieve tremendous efficiency gains, as you would expect. And part of the reason is that these SNARK computations are often highly parallelizable, so you can kind of distribute the work in a cluster. But one key problem is that you compromise on privacy. So if I go to AWS and I'm hiring 10 machines to generate my ZK-SNARK, I have to hand over my witness to them. Right, so this could include the secrets for my, Bitcoin or Ethereum wallet, and that's a problem. Okay, So on the other side of the coin, there is a different work that's called collaborative ZK-SNARK. What this work tries to do is it tries to generate ZK-SNARKs where the witness originally that I'm trying to generate the SNARK with was distributed across untrusting machines. Okay? So it kind of goes on the other side. It says, look, I have 10 machines. They hold secret shares or like sort of shares which themselves don't reveal the witness, but collectively can be used to generate the SNARK. And this work shows how we can generate SNARKs in this setting. But the problem in this case is that the cost of generating the SNARK or the amount of work that each server has to do is exactly the same as what it would take to run the same computation on a local machine. Yeah. Yeah, so this one does not, no privacy, give the witness, someone else is doing it.
But the model is the same in terms of trust, trust the distributed cluster.
Here, everybody's trusted. Here, think about honest majority.
Oh, I see. So they're trusted.
There's no, everybody's completely
trusted efficiency.
Yeah, just efficiency. This one, there's some trust. Also, goal is efficiency, but the efficiency you get is, look, if it took me 1 second to generate it on my system, because I have a small machine, I'm going to hire, a bigger machine somewhere which can run a secure computation protocol to generate it. But the work done by each machine is going to be 1 second. Like it's going to take 1 second. It's going to be the same work as I would have done.
In most of these cases, there's some witness in some places. Then you give it to pieces, or did they generate it already distributed?
Good. So in this case, you have the witness and you give them, and there's no privacy. In this case, they're assuming that the witness is already distributed. Great. So great questions. Thank you. In this case, the cost of each device is the same as the cost of generating proof on with a single machine. A natural approach to do it is like, maybe I want to kind of mix the two together, and rather than having one machine, doing sort of this secure computation or collaborative SNARK between machines, rather we do a collaborative SNARK between clusters of machines, and we can perhaps get efficiency from using DZIC, but sort of the privacy guarantees we want from this work. The challenge, one aspect that is not appealing from a ZK-SAS perspective is that we're going to have high monetary costs, right? So if you imagine having a distributed network of 64 kind of clusters of machines, and each cluster having 50 machines, I'm paying the cost of 64 times what it would have taken in DZIC. So what we want is we want sort of better monetary costs. So we want faster proof times while keeping, while distributing the proof by getting like division of labor. So as I am generating the SNARK over 64 machines, let's say, which we're going to do in this work, I want some division of labor such that each machine doesn't do work proportional to the cost of generating the SNARK locally. So here's our framework. What we're going to do is we're going to have a prover who has an input X and W. It's going to go to the Google Cloud or Amazon and say, please give me access to one large machine. This is a machine that has some larger computational resources, but more importantly, larger memory. And it's just going to ask for off-the-shelf commodity hardware for several other machines. So think about one large device or more powerful device and 63 smaller devices. There's going to be some pre-processing. Let's ignore that. The prover is going to sort of secret share its witness among these devices, and this step is typically not expensive. And subsequently, these servers are going to interact, and pop out will come the ZK-SNARK. And the key properties we want is that the amount of computational effort spent by each of these machines roughly grows with 1 by n or tilde of 1 by n of what the work would have been on a single machine. Okay? So effectively, I'm dividing the work among these machines as this computation happens. So thereby, I am going to get faster proof times because everybody has to do less work. And that effectively, that work is happening in parallel. But because I have n machines now, and the factor is 1 by n, the overall memory blow up and the overall computational cost blow up is only order 1. Okay, so I'm paying order 1 in my costs, but I'm getting 1 by n in the reduction in running time. Yes.
Is the work always divisible?
I mean, this is sort of asymptotically. I mean, there are log-n factors as well. I mean, I'm looking at the higher order terms. And
It's always divide the work among the processors so that you can do the work more efficiently.
yeah, so you know, when the work is very small, and this is an approximation, right? So if you're doing, I'm looking at very large amount of work and n being not very large. So maybe there is sort of some discrepancy. It doesn't have to be exactly identical for every server, just roughly the same. Make sense? So yeah, thank you. Good, and the security in our setting will hold as long as less than n/4 of the parties are corrupted. Okay? So this is our model. In this work, since I'm running out of time, I'll quickly summarize our work. So we construct new ZK-SAS protocols for sort of many popular ZK-SNARKs. So you can take popular ZK-SNARKs such as Groth, Model in Plonk, Groth and Plonk being very widely used out there. And you can fit in the ZK-SAS framework and get a protocol to do SNARKs as software as a service. And we implemented the Groth 16 version for Groth 16 ZK-SNARKs. We're able to reduce prover time by roughly an order of a magnitude. Okay, so and it kind of depends on the constraint size and the many other things, but it's almost always better than an order of magnitude. The sort of two key challenges here, effectively for the ones who are, for the cryptographers in the crowd, we want to do like an MPC to do a ZK-SNARK. So there are two main challenges. One is, SNARKs have cryptographic operations. If you're going to open them up as circuits, it's going to blow up the cost. So that's sort of one challenge. And the second is, how are we going to actually get this division of labor? If so there's some computation, we need to kind of divide it. And for the first one, we're going to roughly do like an MPC in the exponent. So we can pull out the cryptographic operations outside the MPC. And the second, for the second idea, we observed that for these SNARKs and many other SNARKs, we looked very closely at these ones, but for other SNARKs as well, you can take the actual algorithm for generating the SNARK and split it into sort of three key components: fast Fourier transforms, multi-scalar multiplication, and sum of partial products. And what we're able to show is sort of custom protocols that are constant around low communication cost and all those nice features, such that we can get division of labor. So this division of labor then translates to a solution for ZK-SNARKs. Thank you.
Our next speaker is Srinivas Golapati from Google, and